Whisper leak, a side-channel attack on large language models. We'll start with how encrypted traffic can leak information. Then we'll cover the attack itself, how it was tested against commercial models, potential ways to mitigate it, and finally, the key privacy implications.
So we generally assume that an encrypted connection to an LLM keeps the conversation private. Is that a safe assumption?
No, it's not. While Transport Layer Security, or TLS, does encrypt the content of the messages, it doesn't hide the metadata. Things like the size of the data packets and the exact timing of when they're sent are still visible to a network observer.
And what can an attacker actually figure out just by looking at that packet metadata?
The threat model assumes a passive network observer. Think an internet service provider or a government agency. The goal here isn't to decrypt the content, it's to infer the topic of a user's conversation just by monitoring the patterns of the encrypted traffic.
Side-channel attacks on language models aren't entirely new. How is this method different from previous research?
Right. Prior attacks were often focused on reconstructing the exact content of a model's response. This one is different. It doesn't try to get the content at all. Instead, its goal is to classify the high-level topic of the user's prompt, using only the patterns from the encrypted packet metadata. The attack works in 4 steps. First, the attacker observes the encrypted traffic from the LLM's response. Second, they extract 2 key features, the sequence of packet sizes and the time between each packet's arrival. Third, they feed these sequences into a trained machine learning classifier. And fourth, the classifier outputs its conclusion on what the topic was.
Okay, so how effective is this against real-world systems? What was the scope of the evaluation?
The evaluation was pretty comprehensive. They tested it on 28 different commercial LLMs. The target-sensitive topic was legality of money laundering, which they phrased in 100 different ways. To create realistic noise, they used over 11,000 general questions from the Cora dataset. And the classifiers themselves were LightGBM, LSTM, and a BERT-based model. For most of the models they tested, the attack achieved an area under the precision recall curve, or AUPRC, of over 98%. That metric basically tells you how well the classifier can distinguish the target topic from all the background noise.
A 98% AUPRC is a high number, but in the real world, sensitive queries are rare. They're like a needle in a haystack. How does the attack perform when it has to find one sensitive conversation among thousands of normal ones?
To simulate that exact scenario, the paper projects the performance under a 10,000 to 1 ratio of background traffic to target queries. And even at that extreme ratio, for 17 of the 28 models, the attack could still achieve 100% precision. What this means is that an attacker could identify between 5 and 20% of all sensitive conversations with 0 false positives.
Given how effective this is, what defenses were evaluated against it?
They tested 3 main mitigation strategies. The first is random padding, which adds random data to packets to obscure their true size. The second is token batching, which groups several tokens together before sending them. And the third is packet injection, which adds synthetic noise packets into the traffic stream.
All 3 methods did reduce the attack's effectiveness, but none of them eliminated the vulnerability. Packet injection had the biggest impact, lowering the AUPRC by 4.8 percentage points. Random padding was close behind at 4.5 points, and token batching with a batch size of 5 dropped it by 3.5 points. So with token batching, you're looking at a trade-off. You get a bit more security, but you pay for it with higher latency in the response.
Correct. And packet injection avoids that latency problem, but it comes at its own cost. It increases bandwidth usage by 2 to 3 times. So what's the big picture here? What are the main implications of this research? The key takeaway is that this isn't a bug in any one specific model. It's a systemic vulnerability that arises from the way these systems are commonly built. The combination of autoregressive generation, streaming APIs, and the fundamental properties of TLS. The researchers did a responsible disclosure to all 28 providers. The response was mixed. Some providers, including OpenAI, xAI, Mistral AI, and Microsoft, deployed fixes. However, some of the other providers either declined to implement mitigations or were unresponsive. It seems like this points to 5 clear actions for developers and security teams. 1. You have to address metadata leakage at the system design level. 2. You need to carefully weigh the security performance trade-offs for any fix. 3. Use multi-layered defenses, not just a single approach. 4. Recognize that token batching by itself is not enough. And 5. Expand your threat models beyond just content encryption.
The paper concludes with this: protecting user privacy in the age of AI requires holistic defenses that address both what systems say and how they say it.